So we want to look a little closer at the physics of waves, because that is really the basis of quantum mechanics. And I just refer back to when we first talked about waves. I believe we were talking about Maxwell's equations and light waves, and we were talking about different kinds of waves. And the things we came up with were water waves, stadium waves, people waves, string waves, light waves, electromagnetic waves, which is a light wave, and I'm not sure what else, but those are some examples of waves. So the question I have got for you, hold on, is just to remind you or ask you, what is a wave? What is a wave? Right? A wave is a disturbance that propagates through space. It is a disturbance, or what else would I call that? It is a movement of something away from equilibrium, right? That is what I mean by a wave, or by a disturbance that propagates through space. Now, what propagates? The disturbance propagates, but the actual thing that moves away from equilibrium doesn't necessarily doesn't propagate through space. So for a water wave, the water molecules, right? So with a water wave, if this was a water wave that's traveling to the beach, the molecules in that wave, they sort of rotate around, but they don't move from. They don't do that, right? The water molecules don't move, but the disturbance of the water molecules moves through space. A good model of a wave is always to think about maybe a wave on a string. So if we have a string and we fix it in place, some length L, and we want to create a wave on that string, we can go ahead and pluck the string, just like a guitar string or something like that, and a wave will propagate along the string. So there's a continuous wave. So the first, I want to define some properties of waves. There's a continuous wave or a wave pulse. A wave pulse would be plucking the string. If I pluck the string, I would disturb the string in one place. I would have to erase that part down there. Oh, I'm not doing a good job. I would have to disturb the string in one place, and then that disturbance would move down the string and might bounce off the wall and come back, etc. That's a wave pulse, as opposed to a continuous wave, or CW, continuous wave. A continuous wave would be a continued driving of that wave. We would have to continue to drive the wave, like a speaker that is playing sound. A beep would be a wave pulse, but a continuous sound would create a continuous wave. We could create a continuous wave on a string by simply taking any part of the string, and maybe just the end of the string, and just driving it up and down. So if we continually drive this up and down, then what we're going to do is we're going to get a continuous wave instead of a single wave pulse. Now that's just the equilibrium line, and the continuous wave is something that travels up and down. The continuous wave still goes up and down. It bounces off, it comes back, etc. Okay, continuous wave versus wave pulse. There's transverse wave versus longitudinal wave. Do you know the difference? A transverse wave, those are two different types of waves. And for example, a wave on a string is a transverse wave. What does that mean? It means that the wave disturbance is perpendicular, right? The disturbance was perpendicular. Disturbance is perpendicular to the wave motion. This is the velocity of the wave. The wave travels with some speed, I should say, really speed v. But the disturbance is perpendicular to the velocity, I guess, perpendicular to the direction of the wave. A longitudinal wave is where the disturbance is parallel to the velocity of the wave. So what would an example of a, well, actually, let's just, transverse wave. Stick with transverse for a second. Transverse wave, that would be a stadium wave where the disturbance travels around the stadium, but the disturbance is people standing up and down perpendicular to the direction of travel. So that's a stadium wave. A water wave, that's a transverse wave. Trying to think of other transverse waves. Doesn't matter. A longitudinal wave is where the disturbance is parallel to the direction of travel of the wave. And an example there are sound waves. When you make sound, here's a person making sound, and here's somebody over here. Whoops. When you make sound, you are longitudinally disturbing the air molecules, right? So you're squishing the air molecules in the direction of travel of the wave. So this shows the fact that what I'm trying to show as you are talking, you the person on the left is talking to the person on the right who has big ears, that the wave travels in that direction, the disturbance also travels in that direction. Sound is actually a pressure wave, and so there are areas of high pressure and low pressure as you travel along, as this sound is coming out of you. There's areas of high pressure and low pressure as you travel along in this direction. So that's a longitudinal wave. If you have a spring, you can make both longitudinal waves and transverse waves. Imagine a spring, right? Take a spring. I found a great simulation online, so I'll just plug that into this lecture.